Oh, hello. Oh god, wait, why are we- hello? Are we doxing me? Hey everybody, free advertisement for this online store I was looking at. That's not what we're doing today. Good thing that wasn't on any sensitive information. The Bite of 83, why is that capture called that? Hey, how's it going? Jump scare. Damie jump scare. Today we're gonna do something a little different. You know, some VTubers like host watch parties and stuff, right? They'll be like, oh, like let's watch Cars 2. Except we're gonna watch a lecture instead. Basically, I slept through 2 lectures, and the notes I got were not very good from people. So I'm taking it upon myself to fix it. So yeah, we're gonna see how this is. If it's really incredibly boring, then well, we're not gonna do this all the time. So that's my take. Um, let me adjust sound a little bit. That probably is a little too low for you to hear. But I don't know how sound mixing is gonna work, because I'm assuming this is going to be very, very, very quiet. If I had to guess. Okay. We're gonna do... This is, POV, you're me, going to my class. This is... Okay. Let me get through the first...
Today we're going to start on our third.
Oh, is there closed captions?
We're going to.
Let's go! Okay.
Specifically, we're going to be looking at a subtext of that. Or
Okay, perfect. I love closed captions, guys. I love closed captions so much. Okay, we're gonna be talking about... Can I full screen this? Oh, this is so awesome. This is so great. Oh, the top of it is cut off a little bit. Let me fix that for you. Okay, so it's gonna be on moment and shear diagrams, and then we're gonna do normal stresses as well. These actually, I think these links, the videos, like, I could actually link them, because I think they're just open, like, on the web, like, you could find these. But I'm gonna take actual handwritten notes for this, so we're just gonna chill out and do some mechanics and materials, and maybe I'll make some jokes or something. Oh my god, if this guy makes the same jokes he makes every single lecture, he makes the same 3 jokes every single lecture, it kind of drives me insane. Okay, this was Monday. I don't know what date it was. Review on stream. Smiley face. Okay. Okay, moment diagrams. So this is like, I haven't done a lot of mechanics and materials on stream, but... Oh god, okay. They are very quiet.
I'll start out by defining what we mean by beam.
Wait a second. Let me turn this off for 1 second so I can mix this better. I'm gonna turn this way down, turn this way up.
Definition is going to be similar to what we have seen for both the axial and the torsion models. Specifically, what I mean by that is that we'll have a one-dimensional axis, and we refer to that as the predominant dimension, or sometimes the longitudinal axis, as we refer to it here.
Okay, that's...
And in this
I'm gonna turn this up more.
In this case, what that means is that this
oh my god,
is
that's so loud.
length, which we're going to use the variable to describe L. So typically spans of the beam, either short spans or longer spans, will be given in terms of a variable that's their length. So that's the length of the one-dimensional axis.
How are we feeling about
that's
that?
The predominant or longitudinal axis. And then attached to each point along that length, we're going to have a cross-section. And that's very similar to what we saw with the axial model and also the torsion model, where...
the torture model.
The
torture model? Okay, wait, sorry. Okay, so... Basically... torture model is making sense. Okay, prismatic rods vector to transverse loads and moments. Yeah, so... We just have a very long beam that has a very small cross-sectional area. The torture model. Yeah, we have a length of a beam, and like the basic idea is we're just gonna like go along this beam and figure out all of the additional stresses and stuff on it, which is gonna be fun. We can make a diagram for what those things are gonna look like. I have done these, but I like didn't really do them.
Model, we would have a one-dimensional line that was the center of twist, and then attached to it at each point along the longitudinal
They be the type of fellow to go across a beam.
Cross section. Me
when I walk across a beam,
either solid circle or a hollow circle, and that's kind of how we're going to view this too. So we're also going to restrict the kind of the geometry of this such that the cross section is significantly smaller in geometric size than the length.
It's like a spaghetti.
So typically, if
imagine
you
a spaghetti.
drawing a circle around the cross section, you were to take the diameter of that cross section, it would be significantly smaller than the length of the beam. To
I don't know why they always say these things like a million times.
We're going to make later on in this theory.
Like he said that already. He doesn't need to say it again.
Limiting ourselves to setups where that geometric assumption is appropriate. The second thing we're going to talk about is the material assumption.
We always make this assumption.
We've seen this picture before, but just to explain it one more time, the idea is that here is a response that loads and then unloads on the same path. So that is an elastic response, but it's non-linear in nature. We're going to limit ourselves to linear responses, so when we load and then we unload, it loads and unloads along a straight path. And there's no hysteresis or damage. Yeah. It's basically an idealized linear elastic material.
Basically, everything is beautiful and nothing sucks.
The only type that we're going to consider. We'll make some additional assumptions a little bit later. The second thing we're going to assume is that our displacements and strains are small. So if you were to think of a beam, let's say something roughly of this geometry.
These are always have so much time. All the assumptions. There's like 5 million assumptions, by the way.
Angles of the rigid body rotation of the system are going to be very small, such that essentially, if I were to take the sine of the angle, it's approximately equal to the angle as an approximation. That's fairly appropriate.
Small angle approximation.
The reason we don't allow for larger strains or larger rotations angles here is because, if you recall, for the axial model, we had an approximation that the strain, the normal strain in the x direction, was approximated as the change in length.
Why the body rigid?
And we talked about how you could compare that to a
if it wasn't rigid, it would fall over.
For example, include a second order term, which was something like this: change in length over the original length squared. And the idea was that the strain measure that we use when we talk about a linear strain measure only includes the first term.
We don't have to do differential
equations.
That
this term is approximately 0 in comparison to the first term in the series, which is this one right here. Right now, if that's not appropriate, then this theory isn't appropriate, and we would have to use a nonlinear strain measure. So that's kind of what we're talking about broadly speaking. We'll return to this a little bit later. As you go on and learn mechanics, we'll kind of get a better definition for strain. But for
basically,
now,
that's kind
of what we're saying is roughly that the
no.
angle of rotation
we just simplify it so that it's easier to work with.
The angle.
Sometimes
should be roughly
you don't need that extra 5%.
The first order term, where the second order term, this guy right here, is small in comparison to the first one. If those two are violated, then we would turn to a different type of theory. The next assumption that we're going to make is that the members are straight and prismatic. We're not going to allow for curved beams at the moment, so we're going to limit our geometry to straight members, and then you have to define at each point along that length, that longitudinal axis, a cross section, such as shown here. So that'll be the next assumption, and then we're going to consider
like
just a couple of type of loads. So we'll consider point loads. So that would be something like shown here. We'll consider point moments, and we're also going to consider distributed loads. And if you recall, what's unique about this particular set of loadings, if you went and looked at the axial model, here was our bar, and the loads were directed along the longitudinal axis. If you looked at what we did for the torsion model, all of our loads were again directed along the longitudinal axis, so they would be lined up with the predominant dimension, like here.
Limiting their geometry to straight members size walks away.
They don't line up with the longitudinal axis.
You're gay.
So this is the first case in which we've seen.
But it's prismatic. That's like kind of like a rainbow, right?
These three types: point moments, point loads, and distributed loads. The next thing that we're going to do is we're going to kind of neglect how those loads get into the system and how the boundary conditions support the beam. And the reason we're neglecting that for now is because that involves detailing. So how is it bolted or welded, or how are the loads in contact
Saint
with the
Venant,
surface of
crazy
the beam.
guy.
All
He
those
just said,
details
put a
introduce
big metal
local
plate on
stresses
it.
around the region in which
I
they're
kind of love
applied.
that for him.
And this theory is not meant to predict those localized stresses. Those would typically be dealt with in a separate design stage where you look at detailing.
Alright, I keep clicking my pen,
And
probably
we're
really
just going to
loudly.
assume for now that we're not looking at that.
I'm gonna write
and
Saint
that would be
Venant.
handled
I know
through
who
a
this
separate
dude
process.
is.
This idea that we can kind of ignore them while if we're far field of those specific boundary conditions is referred to roughly as Saint Venant's principle. And we're going to appeal to that for now, but
I'm ignoring how loads got there. What is happening? What is this class? Why are loads interacting with each other, Damie? Is this math? Okay, let me explain. What's the best? Let me go over to... Wait, do I have clip up? I don't have clip up. Let me tell you exactly what this class is. Just in like 2 seconds. Or maybe not 2 seconds, that's pretty fast. This is a very simple class. A lot of my classes are like this. Because I'm on the quarter system, we tend to have very simple classes. So it's like this. Okay, the idea is when you're an engineer, so it's a civil engineering class. When you're building buildings, right? Buildings are made out of things called members, which are like beams or, whatever, right? And we want to know what happens if we press down over here, and this is like on a wall. We want to know, like, well, what happens if we press down over here and this is on a wall? Or what if this member is attached to like another member and we press down here? And we press down, but we also press down over an area. Like maybe there's a big block here that's pressing down. And what if also we turned it at the same time? Like we kind of like twisted it. That's what this class is. Literally just that. And so why you might want to know this is because for choosing your materials, like let's say you're building a building, right? And you want this building to be really tall. And you choose like have it be made out of spaghetti, then you can figure out how much force is going to be on the spaghetti. If the spaghetti is going to be able to take that load, right? Like, or is the spaghetti going to break? That's the whole class, basically. You wouldn't want to use spaghetti. You would probably want to use something stronger than spaghetti. I see how I've been pressing on members. I know, it gets a little... There are a lot of vaguely phallic things in engineering. Thank you, Damie. There are a lot of vaguely... What we're doing right now, though, like in this lecture, it vaguely... I know, when we start talking about holes and shafts, it's a little hard to ignore the... You know that I think about, yeah, loads and members, that's kind of... Every time I listen to your stream. The reason why it's so weird what this is like, we're basically trying to make a model that we can use to kind of explore these different forces and stuff. I'm like, what are they teaching this catboy? Me when I'm in my tension class where men press on members to relieve the tension. Men press loads on member. Okay, that's pretty crazy actually. God damn it. But yeah, we're just trying to make a model, so like we have to make a bunch of assumptions. Our model is gonna be like 3 numbers or something, and so in order to get it so easy to use, we have to make a bunch of assumptions like, oh, well, if you have a big load, you can't do this, or oh, well, if you have a really thick member, can't. I have to be so unserious now. I'm not trying to do that.
Directions, and so it's really more than what I had stated before in the sense that it's not only
material
linear,
response is the same in all directions.
It's not only elastic, but we're going to
linear.
assume that it's isotropic.
Oh, I see.
And we're going to assume further that it's going to be the same in tension and compression. So here's an example that this line does not change. So you don't have something like a response like that. That would be a linear response, but it's bilinear because it has one response in tension and one response in compression, which is different. We're going to assume it's linear elastic, isotropic, and it's the same.
Directions as in like.
The next thing that we'll look at is that we're not going to consider buckling. So just to remind you,
I thought he said
about the axial problem. If we loaded the axial problem like this, we could get a form of buckling. And we didn't do any type of analysis on this. We just kind of put it on it and said that that would be a separate stage in the process that you would analyze the system for this type of a global buckling phenomena. Same thing when we got to torsion. If we had a torsional load,
our members stay straight. They do not
put a torque on each end of this. If it was long and slender enough,
like that,
it would be possible to get this to buckle. And it's not. I'm not going to really be able to draw the shape very well, but the idea is that it's a kind of a helical buckling. So looks something like this. So that's
I didn't know it did
buckling you might see in a torsional problem. And in a beam, there's similar type effects where if you take a system and you load it transversely, so if I load it in this direction and I'm supporting it like this, sometimes what it wants to do is it wants to roll out of the plane towards us. So this top surface kind of rolls down like that. That would be an example of a type of buckling that you might see in a beam. It's referred to as lateral torsional buckling. This would be the second.
They're bad
one
beams. These beams don't behave.
Buckling, a helical buckling. This is just compressive buckling in a column or a beam. And each of these would have to entail a separate analysis step, and those techniques will be covered in the second of the mechanics courses in this sequence.
I can't believe.
So for now,
they just go, it'll be the next class, don't worry about it.
Dealt with later. And then we're going to kind of do the thought exercise that we've done a couple times now. And
what do you guys think of this one?
This
is a pretty good diagram.
Loaded, we take the undeformed shape and we draw a grid on it. So that would be this geometry right here. And then what we do is we imagine
it's like a worm. We
load the system and we're going to see what happens to those lines after the beam is loaded. And on the right here, we have shown this. Now this obviously violates some of our assumptions about the angles, angle changes being small, but we've just exaggerated it here to get a feel for what the lines look like in this case.
Kind of
what we're going to learn a little bit later is that these lines that go this way and this way, for example, over here, they're still going to remain straight lines.
Okay, good. They didn't twist
those two lines define is going to be
member has been bent
before and after.
It's like a happy face.
That'll be one of the kind of the kinematic outcomes that we'll have when we develop the theory of this. So visually, this is kind of what it looks like, just for now to give
just in case you couldn't imagine what a beam looks like when it's twisted. Not twisted, sorry.
In the process of figuring out how they deform, one of the things we have to deal with is how they're supported. So we're going to talk about boundary conditions next.
Boundary conditions, everybody's favorite,
and we'll
statics.
Go through some simple boundary conditions. We'll use some symbols here, and the symbols have a very specific meaning that are sometimes counterintuitive.
It's a glimpse into my twisted beam.
Let's take for this roller on the right, for example. In this roller,
it's the Joker. This is a normal beam.
So you would think, okay, well, if I load the beam vertically like this, that roller doesn't do anything, and it would just rotate. It would lift up off of there. That's not what it means. Okay, the symbol, it's just an abstraction. It's a symbol that represents a boundary condition that can provide a reaction either vertical, and it can be vertical up or down, right? So that means that, in fact, this roller could have a reaction up or down. So this would be the unknown reaction.
It's like a magnetic roller. That's what I was
taught. It can't provide a horizontal reaction, so it doesn't provide any resistance.
This is just statics. I don't know why they're wasting time.
Resistance.
Sorry. You guys probably don't know this,
on the
so
other
it's
hand,
fine.
Can provide a resistance either up or down, so a reaction that way, and it can also provide a reaction.
Also, I do want to note, so this video is
reactions here. So
like kind of long, a little bit long. We're already like partly into it. This video is like 40 minutes long. My lecture is 2 hours long, and this video covers the same amount of content. So I'm kind of
fixed boundary condition.
He just starts talking about random stuff sometimes.
Like I'm gonna have a reaction either vertical, right, up or down, horizontal.
To use a phrase, he kind of yaps a lot.
Which would be in either direction. And you can choose whatever direction you want to call positive for all these, because these are external reactions. We're just going to end up solving for them. And similar, if you go down here and you look at this case here, there's an external reaction here, which could be either way.
Oh yeah, cantilever.
The external reaction,
a fixed thing restricts a moment. I don't know if you said that, but I think you probably did.
From the internal forces in the beam. And so what I'm getting at here is that in this particular example, when I look at this roller and I say, okay, well, there's no moment reaction here, that doesn't mean that the beam at that point, which is, let's say right here, has an internal moment equal to 0. Okay, that's a different thing. So we have to be very careful when we deal with beams that we're talking about or distinguishing between internal and external. So the supports are essentially providing us external forces. The loads are essentially external forces, and what
it's not that hard. Just think about if you can move it up or down, and then if you can twist it, and if you can't twist it, then there's a.
But for now, let's kind of go through all the different boundary conditions you might.
If you can't move it up or down, then oh god.
And we'll go through these.
What is
I'm going to add a
okay.
column to this table, and the columns I'm going to add to this are going to be the reaction in the x direction, reaction in the y
Who needs
direction, and a moment.
Wait, what is u
z.
x?
The coordinate system we're using here is this is x, vertical is y.
Okay, sure.
And z is coming out at you, so it's x cross y is z. And what I want to do is I want to put in this last set of columns
maybe it's
whether or not there's going to be a possible reaction in x, y, or moment z. And so we'll just go through them one by one. So let's start with the pin.
Oh, my laundry.
And the idea is that
okay, I gotta go get my laundry. Wait a second.
Is the display.
Oh no, I can't. Oh no. What do I put on? Should I put on Cocomelon? I can't. I'm in the math category. This is also not really math, but we're gonna pretend like it is math. I feel mildly bad that I'm just in the math category with mechanics and materials. But there's not a mechanics and materials category, okay? Twitch, my response, add a mechanics and materials category. I'll stream that. I'm gonna go run and get my laundry. Real quick. Oh, fuck. Okay. Here, wait, I can put on, here, I'll put on an introductory one. Here, look at torsion indeterminate.
We have been working on torsion problems and the torsion model for the last week or so, and today we're going to look ahead to indeterminate torsion. And we'll find that basically it's very similar to axial indeterminate problems, and the fact that you just distinguish between determinate and indeterminate. What the real distinguishment is in the context of solving either a torsion model or an axial model is basically when you do your balance laws and you go through and you do your free body diagrams, you're able to find all of the external reactions, you're able to find all of the internal axial forces in the context of an axial model, or in the context of a torsion model, you'll be able to find, again, all of your external reactions and all of your internal torsional forces, resultant forces, at any point in the structure just using the balance law and free body diagrams. So if that's the case, then when you go to calculate angles of twist, or if you go to calculate stress, for example, different quantities like that, then all you have to do is just take those values and plug into the secondary equations. So the methodology goes, you go from your balance laws here, and you go directly into calculating your secondary variables of interest. Now, when we go to an indeterminate problem, just as the case was true with axial, we find that we're going to have to do the balance laws, but at that point we will not be able to solve uniquely for the internal forces in the system, so the torsional forces in each section of the shaft that we may be looking at. We may not be able to find the external reactions, but we'll be able to express them in terms of a set of unknowns that we kind of have some control over, so we can set up the free body diagram, let's say in terms of one of the unknown reactions and kind of eliminate another one perhaps. But bottom line is at this point we won't be able to get numbers in an indeterminate problem. We'll just be able to get expressions that relate forces at different points in the structure. And then we can use the constitutive relationship, which will relate those unknown forces to displacements in the system. And when I say displacements, we're talking about generalized displacements. So if we're talking about an axial model, that would be an extensional or contractional displacement. So you're talking about a change in length. If you're talking about a torsion model, what we refer to as a displacement is really a rotation. So we're talking about an angle of rotation typically. And we'll be able to express those in terms of the internal forces using the constitutive relationship. And then at that point, you'll still have a set of equations that aren't closed. You'll have more unknowns than you will equations. And so to close the set of equations, you'll have to write down a kinematic expression which relates the displacements. In the context of a torsion model, that would be rotations, so that you can solve the set of equations. And at that point, going from above the setup to down here, when you go through this step, it's basically a linear algebra problem solving for. And we've done this before in the context of axial. So basically, there's kind of nothing really new here. There's no new equations, no new theory. However, I want to encourage you when you go through these indeterminate torsion problems to be very precise and be very careful with your signs and how you draw your free body diagrams, and pay attention to all of the details. The details turn out to be very, very important. So as we go through this series of examples that we'll go through, take a note of how we're drawing, for example, our internal unknown torsional force, so our resultant torsion. When I draw it, note what direction we're assuming it to be in, because that sets up your kinematic equations. So just pay attention to the details as we go through these, and you'll find that it's really not any different than a determinate problem, other than the solution step where we'll have to do linear algebra. So let's go and take a look at some of those examples.
Why am I sparkling on? What's happening? Wait, that was only 3 minutes? Hello? I thought that was a lecture. Did you learn about the indeterminate axial problems? Or maybe he just taught it really fast. Honestly, that's also possible. Wait, that's so sad. Just a glimpse. Sorry, I just saw just a glimpse into my twisted beam. Yeah. Okay, well, I'm back. We're winning. Man, I'm really glad that they have notes that are more than 3 minutes. Wait, are they actual? Oh, never mind. The notes are just really short for that. Maybe it's actually just straight up short. Okay. Anyway, we're back.
In the x direction, so it
locked
can't
in.
Move this way or this way. So we're essentially saying
my roommates have been saying locked in so much.
That's what the word fixed means. It's going to be specified.
Can I get a chicken on screen?
If we know
I really want to cover up some of this with chickens.
We would have to solve for the reaction in
happening?
the x direction. So this would be, yes, we would have a reaction in the x direction that we'd have to solve for. Same thing for y.
Wait, so it's yes, yes, no.
Fix the vertical displacement. So I'm saying I know what the displacement of this point is.
I really want to make chicken. I
So
should make
this
chicken
is
on screen
known.
longer. I
That
think
means
chicken on
that
screen should
the
be longer. What do we
reaction
think?
Over there,
I think chicken on
y
screen
would
is
be
too short.
unknown, and we would have to solve for it. So the answer is yes, it does exist, right? So we'd have to.
I'm gonna make it longer right now.
What about the moment? Well, in this case, it's not preventing rotation.
No.
So what does that imply? That implies that if it's free to rotate, there's no resistance, so we know there's no force. So in this case, the moment about z is known.
That's 2
So
minutes.
do we have to solve for it? And the answer is no, because we would know what it is based on the fact that it's free.
Germa reference:
to rotate.
coffee, Cheetos, chicken.
And so these, what we're
Old
answering
Germa.
in these last 3 columns are: do we have to solve for Rx, Ry?
I'm gonna make it
and
300 seconds.
Z? So I'll put a little header on this.
No, don't exit.
Okay, and you would solve for these using statics. And
Okay, King, can we move past this?
And then lastly, the moment roller. This is kind of like a slotted connection, so it's prevented from
Jeremiah.
It's pretty obvious.
It's a scout.
I'm fixing it horizontally, so
External
I know
work.
you acting through R.
Oh wait, let me actually.
Pattern derived from. The pattern comes from the idea of energy conjugacy, and I would just remind you of what external work.
Well, I don't mind that. I like external work.
So, for example, external work. If I look at the pin as an example,
momentum.
So here at the pin, I am fixing it vertically and I'm fixing it horizontally, so I know UX and I know UY, and I'm going to solve for RX and RY. So what's the external work done by that system? Well, it's going to be UX
R cross F
acting through RX.
Okay, that's fine.
Plus UY acting through RY. Okay, so if you look at this, that's an energy term, right? It's a force acting through a distance. And you'll notice that these terms, they're at the same point and acting in the same direction. So UX is at
this is great, but like we don't need it.
And RX is at the left end of the beam, and they both act in the X direction, so they're both acting this way. Same thing with Y. Y is at the same point.
Y.
UY acts at the same point as RY, so they're at the same place, same direction, and they're energy conjugate, because when you multiply them together, you get a form of external work. And what you'll notice is that anytime you have a boundary condition, you can specify either the displacement variable, or you can specify the force variable, but you can't specify both, so you can't do that. And that's consistent with how these boundary conditions are lining up. If you look at the pattern between these columns over here.
Well, okay, you can't specify both because then it's not a problem. You don't have anything to solve
kind of a general
for.
Theorem. And if you go on to study mechanics and you want to do like finite elements, this is one of the fundamental things.
Oh, I see. So he's saying like, okay, we can
all of those analysis procedures.
Like, let's say we're trying to design something.
Specify energy conjugate.
This is like the behind the scenes. If you're trying to design something, like let's say I'm trying to make let's like I'm working on Ethernet, right? Like I'm making a frame and I'm trying to figure out how to make it so it doesn't break. If I want to constrain, like I can constrain, let's say the distance, the displacement of the frame, right? So let's say I say, okay, well it can move like 0.5 millimeter or something. That's pretty small. Okay, it can move 1 millimeter. Then I would be able to solve for how much force that exerts, that would be internally on that beam. If I said both, it wouldn't be physically accurate, because I would just be giving random stuff. I couldn't be like, well, I want it to displace 1 and also have an internal force of, a reaction force of this, because that's like, you can't do that. But it's just funny to me that he kind of didn't explain it like that. He was like, well, you can't say both. It's like, you could specify both, but like, there's only one physically correct answer.
Terms and the energy conjugate terms.
It depends on what you're solving for.
You can only specify one or the other, but not both. So just a bit of background on where these boundaries come from and how we're going.
This is so funny because this is like my internal monologue when I'm listening to professors. I'm like, well, it's like yes and no.
And be familiar with all of these boundary conditions as we go through them, and we'll see plenty of examples. So the next thing is we are interested in finding the internal forces in these beams. So we have all these external supports, which gives us external reactions. We have external loads, and we're trying to find what's happening interior to the beam in the model, right? So we're going to take free body diagrams, which cut through the model.
Body diagrams, my beloved.
By doing that, we'll be able to solve for the internal forces in the beam. So let's talk about what those internal forces are and how we might solve for them.
Oh,
so
wait,
here we have a free body diagram, and the free body diagram that's shown on the right, I'm going to
go back for a sec there.
And it comes from taking this free body diagram right here. I
just want to see if this is important. For planar two-dimensional beam, there exists 3. Okay, no, that's just regular statics. Okay.
For the internal forces.
Just 2D equilibrium, so we get 3 equations,
talk about what
right?
Those internal forces are and how we
for some forces in X, some forces in Y, and then moments.
So here we have a free body diagram. And the free body diagram that's shown on the right, I'm going to outline, and it comes from taking this free body diagram right here, and we're cutting it with plane BA, and this FBD is showing.
Oh, I remember this vaguely.
Now, what are we looking at here? Well, we have an external force. This is like an external load. And then we have the cut plane, and in the cut plane, we're revealing internal forces in the beam. And the internal forces that we've shown here, we're showing a force which lies in the plane of the cut. That is a shear, right? So shear implies that it lies in the plane of the cut. And we're going to use the symbol V, capital V, for shear in a beam. The second thing we see is that we have a moment that acts on that cross section. So that's this,
this is so exciting.
Right here, M. And for the internal moment, we're going to use M. And so those are the two variables we have. Now, of course, you could argue, well, okay, we know that there might be an axial force, so we might include that if it was appropriate. For this problem, it was left out only because it's pretty clear there's no axial force.
Pretty clear there's no axial.
An internal torque, right? So we might have something like that. And if that's the case, then we would include the internal torque and solve for it as well. But it was specifically left out of this problem because we don't have any torque supplied. So it's pretty easy to see that those two would be 0. So that's the first part, is just because it's not shown doesn't mean it wasn't considered.
So we've been doing all like in the X direction stuff. So like your moments are going to be kind of around, twisting around the beam, lying in the X direction, or your forces are going to be in the X direction, like tension or compression. So the beam is getting squashed or stretched. But now we're kind of like pulling it up or down and seeing what internal forces come out of that, which is exciting. That's pretty cool. Because that happens a lot. You know, like, if this is... I mean, there could be a person standing on there, and like that could be the load applied there.
In general, you're going to consider all possible internal forces. So you might have moments, shears, axial, torsion, and they could all be acting at the same time. And we'll get to problems like that later in the course. The second thing I want to point out is I could have taken the free body diagram from the other side. So if I look at this side over here,
reaction,
and I draw this FBD, I'll draw it down below. What you can see is that I have the boundary condition to the left, there's my boundary condition. And what do I have on the right-hand side? Well,
that's not an FBD because you just didn't free the body.
This cut plane right here, it's still the BA cut plane or AB cut plane, which is the same as this face right here. So those are equal and opposite faces, right? So that means that if I have a moment over here, and that moment, the one I just highlighted, is acting into the paper. So over here on this other plane, it must be acting out of the paper, which means it's going this way.
Okay. And V has to be going the other way as well.
Of equal and opposite action, right? And then what about the shear? Well, the shear over here is acting down, so over here it must be acting up. So that's the shear.
Epic.
And this is the...
I love when physics doesn't get broken.
Just want to take a moment to point out something, that these are equal and opposite to each other based on...
Oh, we don't have the load. I lied.
But
so we just have a reaction.
Internal forces, if you recall axial as an example, in axial we had an axial force that we would call positive, and if it was in compression we would call it negative. So we had a sign convention for what the internal resultant force is. Well, we're going to like to have one, and we would like to have one here for beams as well. We want a sign convention.
Sign convention, my least favorite thing this quarter.
Of what we're going to talk about next.
Oh man, I dislike signs.
If I decide that, for example, this is what I'm going to call positive, I'm going to call that moment positive.
Okay.
You'll notice that, well, then that means I have to call this one positive as well.
What?
Because they're the same moment, right? Just acting on different planes, and they have to go in those directions because of the principles of mechanics. So I've got one of them going into the paper.
Bro, what? That's crazy.
Paper, but we're going to.
That's not a convention. That's everything.
Positive. And so it's a little weird the first time you see it, but that's a necessary construction of this. Same thing. Necessary construction. Here, the shear is going down, and if I choose to, if I wanted to call that positive, then I would have to call this one positive as well, because they have to be the same.
That's so
variable,
weird.
Right? It's not like one could be positive and the other could be negative.
Bizarro world.
The same thing. So that means that I have to have a sign convention that allows for this. So we'll show you that sign convention here on the next slide. And basically what it looks like is as shown here, and as a piece of kind of background information, I'm going to draw the beam.
Oh, okay. Here's maybe how I'll remember it. Let's have this guy shush for a second. So for V, it's like, it's still it's clockwise. Okay, wait, never mind, that doesn't work because it's clockwise. Man, why couldn't they say if V goes up and the other V goes down? Fine. Okay, I'm just gonna have to remember these. So if the V on the left goes up and V on the right goes down, that's positive. And then if the moments both sort of go up, the moments I feel like are easier to remember. Sign convention. I feel like it doesn't really matter that much. Okay, wait a second. Don't quote me on that. It does matter. It just doesn't... Depending on how you do it, it doesn't matter as much. Because it, like, sign conventions in general, it doesn't really matter how you do it as long as they are consistent. Other than the fact, like, some other people are going to be like, oh my god, you are dumb if you don't do them the way that normal people, like, if you called the y-axis x and the x-axis y, then people would just be like, what is going on, you know? But
so here's a beam.
okay.
And I've got some load, let's say some load F.
Oops, that's my messenger
here.
notification.
And the idea is that the free body diagram that's shown above is a tiny little slice of this beam. Okay, so like here. Right, if I pull that
Same value but opposite direction. Yeah, so it's kind of just like, because
up above, except now I'm going to draw
we are cutting the beam
the left side,
in the middle,
where the boundary condition is.
We want to have both of the moments or the forces or whatever on it be positive, unlike, you know, if you have free body diagrams like of multiple things, then you want to say they have like the opposite reactions on them. But since this is like the same thing, we want them to be the same sign, is what I think.
I'm going to draw the little slice in the middle. And then I'm going to draw the right-hand side, which goes out and has the load over at the far right. And here, I'm going to put our load F.
Oh, he's cooking. He's doing a
and we're just going to work our
derivation.
way through this and say, okay, well, what are the shears in this problem? Okay, so let's start on the right. If I sum forces vertically, the shear on the left-hand side in that cut plane must be going this way, and it must be equal to F. So
Can't move the subtitles.
Put this here, and I'm going to say the shear at that point is equal to F. Okay, then the argument goes, well, this face is connected to this face, so I must have an equal and opposite shear, which is going this way, but it's also equal to F in this particular example.
There's an infinitely small bit?
And then if I sum forces vertically on this cross section, and again, we're just looking at the shears, we're not looking at moments right now, then I would say, okay, well, I have to have a force here, which is also the shear. And then lastly, by Newton's principle, I have to have a shear that's acting this way. And if you were to imagine taking a close-up view of this middle picture, okay, this middle picture right here, that's what's shown up above. And this is what we're going to choose to call positive.
Okay.
Notice that, as we talked about in the previous slide, the fact that this is going down and the fact that this is going up,
never mind,
doesn't change the fact that they're both considered a positive shear. So what's the distinguishing characteristic? Well, this one here, for example, in this big picture up here, this one is acting on the cut plane, but it's on the right side. So it's on the plus X of the side of the cut plane. This one is on the left. Okay.
Oh man, that's a little.
Because of the and it has to be that way because of the logic that we used in kind of sketching out this progression right here.
Because it's the left.
So one of the ways that you can think about
It's
this
positive,
is if you take a little cube of the beam, so like we did here, take a little section out of the beam. Here's our section. The shear that's positive would cause this to spin into the paper. So if you're using the right-hand rule, into the paper.
Oh,
so this
wait.
would cause this little cube to spin like that. And you notice that this shear does that, and so does this shear.
Yeah,
so
wait, I was kind of cooking there.
Action. And sometimes if you want, you can just remember if you're cutting it, if you're on the left cut plane, the shear is up. If you're on the right
the issue is that like
down.
into the paper is usually negative.
Remember, but it's pretty simple once you've seen it a couple of times. The argument for the moment sign convention is very similar. So I'll just sketch out.
They go like both up.
Something for that. Let's say we have.
Okay, well.
I'll use a different example.
It's a little silly, but.
So let's just say we had some moment acting here, and its value was 2. And I'm going to take the same as this has to be the way this say that. But basically on here, so maybe I've got this long beam like this. It has some loads on it. It's got maybe moments. It's got point loads. It's got all kinds of things going on. And what we're going to do is we're going to take one tiny little slice out of this. So let's say this little slice right here. And we're going to pull it out. And that's the free body diagram shown down below. All right, so now that I have this free body diagram shown, what's in it? Well, I have the distributed load. On the left-hand side cut plane, I have shown a positive shear, which would be going up.
Like how they just put everything into one big soup.
Okay, and I also have a positive moment. So this is the moment shown here, so that's this M. And those are the values on the left-hand side. And this thin little slice, its width is an increment, delta X. And the argument is that, well, on the right-hand side, I also have a moment and a shear, which I'm going to assume
a lot of action on that member.
This direction and this direction.
You're so right.
Except here,
I wish I didn't. I wish it wasn't said like that, but you're so right.
I move, the moment is a function. So if I have on the left the moment, on the right I have the moment plus an increment in the moment. That's this delta M. Likewise, if I have the value
it's a
of the
load.
shear
It's a
on the
distributed
left,
load.
On the right-hand side, I have the value V plus an increment in the shear over the distance delta X. So that's the kind of equilibrium argument that we're drawing, pulling out this little slice, and we're saying that the moment and the shear can change along the length. So basically, they're functions. All right. Now, with that being said, we can just apply equilibrium to it. We don't have to really think too deeply about it. And if we do that,
it's not that deep, bro. Don't think too deeply about it.
To this expression, if we take the limit as the increment, delta x goes to 0. So basically what this is it's the increment in the v divided by the increment in x is equal to negative w. But if we take
w?
The limit
As
the
the distributed load
goes to 0, we get the expression shown there. So what does that mean? Well, it's telling us that the slope.
Wait a second. Hold up. We're summing the forces in the y direction. Oh wait, never mind. I was like, why is it the distributed load? And it's the distributed load because literally it's in the y direction. I just saw the bar across the distributed load, and I was like, oh yes, in the x direction. We have no forces in the x direction. Okay. And our moments are just not in play yet. Okay. Dude, I was tripping, I'm not gonna lie. Oh my god. Okay, so we would get delta v equals w delta x, and then so dv dx equals negative w. Yeah, so the slope of the load over the x is going to equal negative w. So like the what's the word? The multiplier of the distributed load, the distributed load. The power? No, the magnitude of the distributed load. That's what it is.
Shear is equal in magnitude to the value of the distributed load. So I'll just shorten this distributed load value. Okay, so we have a a differential relationship between the internal shear and the distributed.
I love how it's like a differential relationship. Like, bro, it's just a slope.
We can sum moments. And in this case, we have this little point on the right that we're going to use, this point O. We're going to sum moments about O and repeat this same argument. And we do that over here.
Some moments
so
about
here's
O.
some of the moments about 0. And now what shows up in this is we have a couple of terms. We have obviously the moment terms. So that would be this, this, and this. But we also have the shear term times its increment. So that's this force times this increment. It's going to give us a moment about O, so it's going to be going.
What's
up
with that W delta X squared?
The sign here being negative. And then the last thing we have is we have the distributed load. So the effective force caused by the distributed load acts through this point, and its distance is delta X over 2. So that's where the 1/2 comes from. And the value of the total force is W times delta X. So basically, this here is 1/2 delta X. That's the moment arm times Wx, which is the value of the force. Now, if we take the limit as delta X goes to 0, we're going to neglect basically this term. This term is going to drop out because it's going to go to 0 much faster than the term that has delta X in it. And we'll make the same argument as on the previous slide that
we are not able to see the bottom of this slide.
Take the limit as delta X goes to 0, so the increment in the moment divided by the
oh my god, having subtitles in a lecture is so nice.
And so what we find,
it just equals V.
On the previous slide,
is
yeah. Of the moment, which is the internal moment, is equal to the value of the shear. And that's the internal resultant force, the shear.
Yeah, we'll get to do some practice.
Relationships.
I'm going to do some practice problems in between these.
It says that the slope of the moment is derived from the value of the shear. So we're going to use that fact quite a bit to essentially solve for moments and shears and beams. And just to kind of take a step back, what's the reason for doing it? Well, the reason ultimately is we're going to use these moments and these internal shears to calculate stresses. So that's what we're after ultimately. Okay.
Good, big picture.
Let's take a moment and just kind of re-express these two relationships that we found, these two derivative relationships. And we're going to do that on this next slide. And the idea is that if I have this relationship that the derivative of the shear is equal to the negative of the value of the distributed load, I could rewrite it to essentially express
what the hell, man? I don't need all this.
Of the shear. So to give you an idea of what this means, I'm going to draw just a made-up problem here, so I don't read too much into this. So I'm going to plot vertically.
This is actually, you don't need to say this. I mean, you can say it.
This W function. This should be a plot of what the distributed load looks like as a function of position X. And let's just say that it looks like this.
Basically, we're gonna graph
this is the value, and it goes from
our loads, and then we'll turn them into moments based on the slope. W funk. I saw that.
Point that I'm interested
even I'm funking it up.
A to B. Okay, so those
to be or not to be.
In. And so I'm looking at this region right here. I'm going to highlight the area.
Plotting W.
Okay, the area under that curve, what is that? That's this term right here. Okay, so the area under the distributed load curve works out to be equal to what? Well, it ends up being equal to the change in the shear between point B and point A. So basically, that right there, this area, is equal to VB minus VA. In other words, the change in the internal shear between points A and B. Okay, so it's you know, in one sense, it's a differential relationship, and if you rewrite it this way, you
needed
can
to
see
prove that. Sure.
And that's more often how we use it, is in this form that's shown on this slide. We can kind of flip the script, so to speak, on the moment expression also. So it's same idea. So if I were to plot here,
well, okay.
Let's say we had X, and this is the shear.
Well, this one we actually use.
The shear function.
But it's also like
is a constant. Let's just say as an example.
kind of intuitive, right? Like if your moment is going to be sort of like a derivative of your v, you're going to be using like the area under the curve to get your stuff.
It's going to be equal to the change in moment, or
like you're just gonna find a load for W most of the time. Like you're gonna
change in moment between A to B, right? So it doesn't give us the value.
We're gonna basically when you have a distributed load, right? That's like a load that's acting, a force that's acting over an area, whether that's just a single area, like a a 1D area or a 3D area, 2D area, whatever. Well, it wouldn't be a 1D area, that'd be a point. A 2D area or 3D area. You sum up the entire load, and then you place it on the centroid of that load, the center of gravity of the load. So if it's a square, you'd place it like right in the middle of the square, right? Or if it's a circle, you place it right in the middle of the circle. But yeah, normally we just do that. We don't need to say like the area under W because we don't need to integrate our W's. We just kind of only have constant W's, which I guess is kind of sad, but you know.
Value, it gives us the change in moment. And so that's the second interesting point that comes out of this. So where did these equations come from? Just to remind you, they came from balance of angular momentum and balance of linear momentum. So some of the forces basically and some of the moments. And so they're very fundamental relationships. There's nothing special here. But we're going to use these over
nothing
and over
special
again
here. I think it's beautiful. Okay, I think they're very special.
We'd like to be able to construct these
just
functions
funk the W
for the internal moment and the internal shear as a function of position. So that's kind of the goal temporarily. And the reason why is we want to be to know the distribution of the internal forces. Okay, and we want to find maybe the max values, and sometimes we're going to see. Sometimes we want the minimum values as well.
Yeah.
But we'd like to know if the beam goes from 0 to L, if that's the beam on the x-axis, I would like to know.
The beam is getting dangerously close to the subtitle.
Moment. So maybe this is the moment curve. It's probably not going to look like that very often, but that's the idea. Like, what is it? And it's going to be some function, and we'd like to plot it over the length of the beam. And the same thing with the shear. We'd like to plot what the shear is as a function of position. The reason we're after this, again, is because this is the first step in trying to figure out what the stresses are at every single point in the beam.
Damn, bro, every single point in the beam, that's like so many points. I don't know if we like really need all that.
Failure calculations, all kinds of, if we want to know the strains, we would have.
We could just do a couple. I feel like we could just do a couple, you know.
Is that we would have to plot the moment and the shear diagram. Even if we weren't interested in stresses and strains,
every single point.
If you wanted to know just what's the displacement of the beam, like how much is it deforming, you would need to know the moment
in the beam. Okay.
As well.
Okay.
So
Okay.
Like it or
Jeez,
not,
it's like in dynamics. We started doing rigid bodies.
You have to be able to draw them.
And it's like,
figure out stresses,
okay, there's only one omega for every single angular. Like, there's a different v, but they all have the same omega. So you can't be putting a million omegas. And I'm like, I don't want to put a million anything in a problem ever.
I will point out before we get there that one last thing is that we're going to take three.
There's only one omega, exactly.
Solving these problems, and I'll just kind of sketch out what they are for you here in the shortest way possible.
The omega
so the
in dynamics
that we're going to use is just straight free body diagrams. So you'll notice I can just take a free body diagram and solve for the moment and the shear at any point in the beam.
What?
And if I do it at enough points, and I have some intuition about
me when I'm an angular
what the
velocity
of the moment and the shear is based on those differential relationships, it's pretty straightforward to figure out the moment and the shear diagram at every point. As a matter of fact, I could get equations for the shear and moment diagram in the beam.
Okay, now he's just
free body diagram.
Now he's just going off.
So the most fundamental way is the free body diagram. And it's important you understand that, because we're going to learn some other techniques. And
I don't know how you would.
The other techniques.
I don't know how you would do it other than free body diagrams.
Forget like what's another way to do this? And the thing that always works is basic statics and free body diagrams. You can always use those. The second method that we're going to use is essentially an integrative approach. So we're going to use the differential equation.
Sorry.
So I'll say that
I do like
integration.
I do like integration, but the way they talk about it is so boring.
So here we're going to use this relationship dv dx equals negative w, and dm
yes,
dx
we like combine
is equal
both
to
of
the
them.
shear. And so, for example, if I knew the
Okay, I
distributed
think-
load, I could just integrate it, right, and get the shear function displacements.
Or graphical. We did it, gamers. Okay, let's pick a fun problem. Okay, sorry. Let's do this one. This is fun. Negative W. Me when I take an L so bad it's actually a negative W. Let's do this one. Let's ball. Let's ball a little. I cropped the wrong thing there. Don't know why I cropped my sound redeems. Alright. Oh, let's head back over to the whiteboard. Here we go. Okay. Let me move this out of the way. Alright, so... let me... oh my god! Wait, metal pipe actually worked to be loud? Wait, what? How did it work to be so loud? Normally metal pipe is like so quiet. Oh wait, because my actual computer volume is up very high right now. Normally I can't hear metal pipe. My member. Sorry. Damn it, keep a hold of your members. Constrain those guys to the ground. Why is this written in blue? Okay. Alright, let me turn up this music just a little bit. Of course it's this song. Always this song. Okay. So we need to start by doing some free, well, we need to start with like drawing some shit on this. So there's a reaction here. I'm not even gonna bother drawing the reaction in X because. Hi. How's it going? We're doing some mechanics of materials. Let's call this. I guess there's a moment here too. Look at all those arrows. I know, right? The distributed load over 35 feet. Okay, so we got that there. We got this here. We need to, I guess, go and cut in between here. I think is the way we do this. Like we were doing with those diagrams. I don't know if I need to draw the reactions. I probably need to find the reactions, right? Wait, but if I do statics, it's like indeterminate. I'm already stuck. I love that. Let's maybe just do this one. Let's start with that one. Wait a second. I have an example. I did one of these before. Let's see what he did first. Okay. Oh my god, what is this? Okay, no, yeah, okay. We did equilibrium. This is scary. I drew a lot of scary things in this lecture. Okay. Okay, so we kind of split it down like in between each thing. So there's gonna be these kind of distinct segments here. Right? We okay with that? Yeah. Okay, so we take this segment of the beam. There's a reaction here. And did we take the one at B? No, we're gonna like go right before B. So it's gonna be like right there. Like that sort of. But we're gonna assume that it's like right here, you know? But I'll do this. Okay. So we're gonna have our up down type thing. So this one's gonna go up, I guess, and this one's gonna go down. And then our moments, let's say they both, well, okay, let me maybe start on the other end. Because I might actually be able to get these moments correct. Semi-correct. Okay. We have an up arrow going this way, 180. Whew. And then we have, okay, so the force is gonna go down. That's our V. Our V, I don't know, C. And then we also have a moment that's gonna go, well, if we sum the moments, that one's gonna go, that one's gonna go this way, so we need this one to go this way. Moment, C. Okay, so we can do the sum of forces in Y, C. Sum of forces C, Y. Sum of forces, yeah, C, Y equals. Sum of forces Y, C. I like that better. Equals 0. We're gonna have 180 equals VC. Nice. We want to do sum of forces. Sorry, sum of moments about C equals 0. That'll be 180 times 20 feet equals moment C. So moment C equals something. 18 and 18 is 32. 32 pound foot. Good to keep your units. 180 BC. Okay, nice. Nice. We're winning. So now we have to figure out figure out these boys. So this is MC, and then B is gonna go up. Oh god, my thing is getting a little cramped. Okay, where do I put RB? Oh, okay, wait. Wait, maybe I can just make a free body diagram for the whole thing? No. No, I can't. Maybe I can. Wait, maybe I goofed it, guys. I might just make a free body diagram for the whole thing. And not split it up. I just do a big equilibrium? No. No. I feel like with the reactions, I mean, I have to put them somewhere. I mean, I could just directly put it on RB. That'd probably be smart. Wait, I like how it gives... I think it gives the centroid right there, that 1520. No, it doesn't. What am I talking about? Those would be equal if it gave the centroid. Why does it give 15 and 20? That's kind of silly. Okay, let me see if I'm supposed to do this by splitting it up or by doing it. Okay, no, I do not split it up. I'm goofy. So we don't have to put any... Oh wait, yes we do, yes we do. Wait, what the heck? Oh, global. Oh, I see. And then FPD injection. Okay. I think I might still be able to get the... equals negative 180. Yeah. Whoops. 80x. Hello? Okay. This is slightly more complicated than I thought. Okay, let me get rid of everything here. Or just delete everything and start anew. Okay. So. Okay, let's draw on the reactions. Sorry for my Discord messenger. Okay. We got 2 reactions. And then we want to do... Yeah, so some of them... So global. Okay, I don't want to put global EQ right here. I'm going to put it off to the right. Because I need space to draw the thing. Oh, I see. We want to draw the graph here, I guess. Not the... I was a peasant for thinking we were supposed to draw three-body diagrams underneath it. It has to be the graph, the load graph. Here, here. He's 0 by the time. Okay. Start to 0. No, it doesn't. I lied. It's gonna start at... Wait, no, it does start at 0. It does start at 0. We just go, uh-oh. It's taking a long time to save. Oh, we're good. Okay, I was really worried it crashed. Okay. Some of the moments about A equals... okay, so we have 10 RYB plus, oopsies, RYB is not in that direction. Minus 10 RYB plus 180 times, let's see, 40, 20, 20 is 100, 115. So RY equals, let's do that out. Okay, we got 180, so 115 divided by 10. 2070. Is that true? Nope, because I forgot my, we also have to do this one. So this is gonna be, okay, 10 times, oh, I'll do that over here. So that's gonna be minus as well. Minus 10 times, 10 times 35. Woo! Times, and then let's see, 35 divided by 2 is a number that is not coming to me instantly. 17.5, I thought it was that. I thought it was 17. Worth. 0.5 plus 40. Okay, this actually might go upward. Let's see, so 180 times 115 minus 350 times, what did I say? 17.5 plus 40? 57.5? 575. But like, that's also not, wait, 57.5? That's not right. What's happening? RB. Why is it? Oh, because it's divided by 40. What am I talking about? Not 10. Also still not right. What is happening? Let's check my numbers. Okay. I'm gonna redo this real quick. Okay, so we have 40 RE minus, okay, 10 times the distance it acts over, so 350 times the centroid, which is 40 plus 17.5. 57.5 plus 180 times 40, 20, 115. How is this not right? I like just plugging numbers in and like slowly going insane because I know like they're right, but expecting them to be something else. 14 point... I'm getting 14.375, which is not correct. Why? Am I missing something? Am I not doing the centroid right? Oh, it's not 32. Wait, did I say 32 divided by 5? No, 35 divided by 2. Where is 57.5? That is from the centroid of this. So this is 35. 35. And then we divide that by 2 to find the centroid, since it's a evenly distributed load, so that's the 17.5. And then we say, how far is it out from the moment arm? So 40 plus 17.5, which would be 57.5. I think. Am I messing up? No, units look fine. I don't know how they're getting... Ah, gotcha. Yeah, at least I think. They're getting 75. I don't know how. Not sure. Really shouldn't be getting a global FP wrong. Wait, maybe I'm just adding. Let me try this. Okay. Yeah, that's 95, not 115. I love doing basic math wrong. Yeah, 40 plus 40 is 80. Whoops. Don't know why I thought 40 plus 40 was 100. Whoops. Here we go. 95. Oh! Oh, wait, divided by 40? 75. Okay, good. We're winning. 75.625. And it does actually go down. So... negative 75.625. Wait, why did I get a net? Oh, no, it's fine. It's positive. Because it was on the same side. We're chilling. So we do sum of forces y. Mm-hmm. 5 plus the 350 minus the 350 times just 350, and then plus 180. So our YA should equal, I'm gonna do plus 350 minus 180 minus 94 point, yes, 94.375. Okay, we're winning. 94.375 pounds. Okay, so we have these. Now we can start to finally do stuff. So for forces, we're gonna go we're gonna go up. So this is our 94.375, and nothing happens after that. So we go to this point, we start at 0, we go up, gonna go over, and now we have this distributed load. So actually we go up again because we have this 15, not 15, this reaction here. So this, we go here. Now add these two. $170. And then we have this distributed load. So as we go across over here, we're going to be 350 lower. So 170 minus 350 is acting on the opposite direction. So negative 180. Here-ish. It doesn't have to be to scale. And the slope here is going to be negative W, I believe. Oops, I don't know why I wrote that there. Here. Yeah, so the slope would be like And then when we hit this point, nothing is going to happen. Go over, and we go up 180. Look at that. We got back to 0, so we did it correctly. And you see we have a closed loop. We start at 0 and we end at 0. Great. Okay, now we have to do the moments. So that's the V. And for moments, our sort of guiding equation, like we saw in the video, in the lecture, is guiding equation is the fact that the slope of the moment equals the slope equals the load. Here we go. Extend this out a lot, and then moments. All right, so we still start at 0. Then we're gonna go to. Remember how we did this. Oh, it's the area under the graph that we add. So this one is gonna be. Okay, let me like label these. 1, 2, 3. Okay, 1. And because this is a force times the distance, and that's a moment. So, times 40. Gonna be kind of big. 3, 3. That's really big. Is that right? Yes. All the way up here. And we'll just pretend. 3, 7, 7, 5. And 94. Then we go to do area 2. And we need to find where the intercept is. Which is just, you know, peachy. That's just peachy. So let's find the, oh, well, I have to find the intercept first. So it's like y, or x2. It's 2, 3. Would be... Alright, so our line is gonna be y equals mx plus b. So 170 equals... or y plus 170. Because when y is 0... Wait, when x is 0. Negative 10 x plus 170. There we go. That's right. Y minus this would be 0, and then so when y is 0, x equals negative 170 over 17. So a2 equals 1/2 170 17. One, 4, 4, 5. Alright, so that is gonna go to here. And we have a slope here, so I'm gonna leave it sort of resident sleeper. Damie. This is, dude, the person I asked for to get notes from his class, they sent me some problems, and I was like, oh, were we only doing problems? And they were like, no, I fell asleep during the explanation. Like, dude, I'm dying over here, please. Times, okay, 17, what's 30, 5 minus 17. 18. I don't know why I had to calculate that. Oh no. Okay, to be fair, you know, it's a 7 a.m. class. It's early in the morning, but also I was like, if you're gonna oh wait, I have to go down from like if you're gonna go to class and you're gonna fall asleep, like just go home and sleep. That's what I think. You know what I mean? That's what I do, at least. Like, that's why I didn't go to class. I feel like it's so much more disrespectful to the professor. Okay, the slope is very large up here, which means that the moment is going to be large, and it is decreasing like this. No. Yes. No? Maybe? This, and then the other one. Wait. Wait, I'm thinking. Moment should increase on that interval. No, because so the load is going in the other direction. So it should decrease. Should it? Okay, it might not. It might not decrease. Let me think about this. Wait, what is it doing? Let me get rid of this. No, oh, the area of the graph is increasing? That's true. He gets up at 4 a.m. to get to math lectures on time, dude. That's like, just don't sleep. You're right, that area is increasing. Okay, there's a different reason why, and I should figure this out. I think it's because, let me think, so... Because there's gonna be a negative moment at some point. Unhinged behavior, yeah, that's crazy. Oh, it goes down because it's in the negatives. Lol. It goes down after. I was like, that's, why is it doing that? So 3775 plus, what do we... There we go. 5520. Yeah, because it's going down to 0, and then we go up to a negative value. So this minus 1620. Perfect. Okay, it's a little goofy There we go. And then last one. The music, I love the tulip music. Okay, perfect. Yeah, because this is negative, so we go down straight across like this. It's like a hat. Perfect hat. Or like a crow, you know? Like here's the eye would be here. The beak. And that's the neck. I'm sure my professors love it when I do this on, you know, diagrams. I just think it looks like there's no harm to it. You can still see the diagram, you know? It's still there. Ooh, Corvid Coon. A lot of work. That's a lot of work for one problem. Kind of goofy, kind of silly. Okay, let me see. Let me do a torsion indeterminate first. And then I might do another one of these. Oh, I see. Oh, these aren't... okay. I just don't know what he might give, because he usually tells us during lecture. Composite. Are we doing composite wrap problems for the quiz? I don't know. Well, maybe let's do a composite wrap problem. Evil mode. Me when I do an evil torsion indeterminate problem. I'm going to create a problem where the inner and outer materials aren't fully bonded together, and then you won't be able to solve it in undergraduate. Then you'll have to stay in school for longer. The real evil. Okay, these ones are fully bonded. Despicable. Alright, stress gauge, strain, determine the magnitude of the load T round to the nearest minute. At point, so point P in the middle of it. How do I do this? Let's think. Okay. Well, we always start with equilibrium. Why am I writing in red? That's evil. First you don't succeed, always equilibrium. We have our big boy. And it's gonna have a torque here. And a torque here. Now, I'm not exactly sure where point P is. I don't know if it's inside or on the outside or like what's going on with that. So this is gonna be our torque out. Well, I guess it's kind of like this. Like that. Or I can do the statics. Out, and then we have our little boy. And then T. Yeah, so right now we have two unknowns and we can't solve for them. So we have to... oh no, I think I know how to do that. Yeah. We'll have to use the fact that they both deform the same amount. So okay, let's just set up our equations. So some of the moments, I guess, equals T minus, or T out minus T, so T out equals T, and then T inner, proper about it, in minus T, in equals T. So they both equal each other, which makes our problem solving easier. Let's see. So then we have to do constitution. So the angle of twist of out equals the torque times the length out, which they don't give us, I guess. It'll probably cancel. Okay, this isn't really too much of a determine, except I don't know where P is. P might be in the middle, but we'll figure it out. Okay, G. Okay, it's a different one, and then I just wrote gout 1/2 pi r to the 4th. Okay, I could just write equals T L over G 1/2 pi r to the 4th, and then all that with respect to the inner. Okay, so we can start filling some things in. So T times L out, or it's actually just gonna be L because they share the same length in that diagram. This will be 160 gigapascals, so 160 times 10 to the 9th times 1/2 pi, and then we're in millimeters, but I'm gonna do meters. So that's, oh god, we have to do the thickness of the walls too. Okay, that's, oh, that is for the outer. We have to do 11 times 10 to the 3rd minus 8.5 times 10 to the 3rd to the 4th. You know, just normal numbers. And then T, right, L over G times... The thing is, when I set these equal to each other, T's are gonna cancel out. What's up with that? I mean, I guess I could say torque is equal to force over area. And then just do one of them? Because normally, like... Okay, I might be missing something. But we'll keep pressing onward. 80 10 to the 9th. 1/2 pi inner 8.5 negative 3rd. Okay. Wait, yeah, it's negative 3rd. Okay, we're good. Okay, we got that. And then kinematics is that because they're bonded, the angle equals this angle. But see, then if I try to solve for t, it doesn't work. I just get the two numbers are equal to each other, and clearly that's not right. So what am I missing? I'm missing something with this tau. They give us a tau. And we know that tau equals TL over... What is for? TL over J? No. How? Let's see. What is the equation? None of these things? I'll look it up real quick. Oh wait, let's see. Oh, we can't do that. Okay. I figured out what we goofed on, but we're good. I was close. I have to put them together. I can't do two separate free body diagrams. And my notification. Stop that in a second. Give me one shake of a rat's tail. Find this thing and then I'll turn. Where's my tau at? TR over J. So not what I said. TR over J. Let me turn it. My bloop bloops. Stay winning forever. One thing. Right. Okay, so instead of this, we're gonna do this. We're going to, in a crazy, unprecedented turn of events, we're going to actually put this inside of this. There we go. This will be T out minus T plus Tn. The T out plus Tn equals T. And then we'll get these in terms of this T in, and this will be T minus. Also, T out equals T in, or I guess we could just do this one as T out. T in, T minus T in. T out, sorry. Wait. T in equals. Oh. That's weird. Oh no, yeah, T minus T out. There we go. Trying to figure out in my brain how that was gonna work out. There we go. Like that. And then when we set them equal to each other, stuff will start canceling. And I think, well, but I don't know about the. I think that we'll have to. Oh, I guess we just have to use maybe T outer equals the TR over J to get that. T out over. Let me plug in these numbers real quick. Oh god, okay. 160 to the 9th times 0.5 times pi times a negative third minus negative third to the 4th. 9 point. T minus T out over this whole thing, and I'm just gonna switch out the 160 for the 180 for the 80. Oh wait, actually, it's okay. I can just delete all this. Oh, that seems wrong. 655. Maybe not. I could be right. Oops, not 6.6, just 6.97. Alright. Then, what are we doing? We're doing... Well, still, it's definitely this, but I don't know if I've used the outer or the inner. Let me see. This. Oh, T out. Okay, so it is T outer equals the tau. Yeah. So T outer equals tau J over R. I believe. Let's see. So that's gonna equal, what do we say? megapascal 60 times 10 to the 6th times 1/2. And then the 11.10 to -3 minus 8. Alright, I don't know if I have to do the biggest one. Probably the biggest one. It seems like it might be on the outside. And then over R, so that's I can just make this to the 3rd instead of the 4th. Say 6 out plus 9 7 equals 9.817 T. T equals, I don't know, there could be a lot of things I just did wrong there. 60 times 10 to the 6th times 0.5 11 to the negative. Okay. Not promising. Times 655 plus. Actually, this seems like a lot. Yeah, so I got 9.6. Yeah, that's not right. I got 9,600 Newton meters. Yum. Oh, that's not great. I probably just messed up some math in here somewhere. Let's see. It could honestly be the radii as well. But it could also be the fact that I used like the what's it called? The outer radius? Like for this one, I think this is this. For J. But oh wait, this is J. I can't do this. What was I thinking? This one is definitely this. And then over. Now the radius, I don't know, that could be not that, but I'm gonna try that. If I do 60, I'm just gonna do everything. 60 times 10 to the 6th times 0.5 pi times. Actually, I'm just gonna, here, I'll do this. There we go. Oh, that's actually a nice number. Times that. Times this to the 4th. And this divided by 11. Okay, this seems much more promising. Yeah, 0.33. Okay, that was definitely it. Okay, so it's gonna be 655.97 plus 9.817 E out equals 9.817 E. Perchance? Okay. Ooh. Okay, it's not the correct magnitude, but it's closer. There's probably something, it might be this radius that's goofing it more. Because it would be a bigger number, I think, if I had a smaller number on the bottom. Maybe we try this? Try that. Boop, 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 boop. Oh, I'm deleting everything. We divided by this thing instead. Oh, my calculator's almost out of battery. Okay, 1.47. This times this. I don't know, I'm shooting in the dark here, but Oh, oh, oh. Okay, it's close enough. I think it's close enough. Yes, okay, so that's what it is. So this was like 1.47, and then t equals 106.72. Okay. I think that is a pretty good place to stop, to be honest. I think that's epic. Swag, even. Yeah. That was fun. I think I'm gonna call it. I gotta go get some food, eat some stuff. Thanks everybody for hanging out. Especially when it was just boring. I don't know, maybe it's fun. Maybe it's chill. Alright, mate. Yeah, I'll be back. I don't know when I'll be back. I have a lot of, thanks for streaming. Enjoy the foods. Of course, of course. Always my pleasure. You guys keep me sane, to be honest. If I had to just be alone with my engineering, then I would become Plato's allegory of the cave. In the sense that I would live in a cave. Alright. I'll see everybody later. Enjoy your day. Stay hydrated. Stay safe. And yeah, you have a great rest of your Tuesday. Bye.